You're listening to the FQxI podcast. Today.
But more generally, I think what is really fascinating to me is to try and use this as a first step of this bigger theory about programmable machines and programmable constructors that could be a bit of a hybrid between quantum computers and biological systems.
A conversation on irreversibility and constructor theory with Chiara Marletto and Vlatko Vedral.
It seems to me that this is the most exciting question in science, right? From kind of micro to macro. Can we really connect the laws of nature in this way? And rather than have them only apply to physical systems, to chemistry, to biological systems, and so on, could there be kind of a unifying framework for all of this?
Yes, and I think there is one thing that you, Vlatko, like a lot, which is this trying to have a better understanding of this transition from non-life to life.
That's it.
I'm Zia Morali. Welcome to a special edition of the podcast from the Foundational Questions Institute, the first in a series of conversations on the topic of irreversibility, with this episode featuring Oxford physicists Chiara Marletto and Vlatko Vedral. Regular listeners will have heard Marletto on the 31st of March edition tease this series of in-depth chats, which she developed with reporter Logan Chipkin. The laws of physics at the microscale are reversible, equally likely to proceed in the forwards or backwards direction. Yet, as will be discussed, the universe is filled with irreversibility. This series includes a number of scientists in different fields who are trying to understand irreversibility, but in less traditional ways than usual. In part 1, Logan speaks with Marletto and Vedral about a number of developments in Constructor Theory, a newly proposed theory in fundamental physics. These include a novel unification between information theory and thermodynamics, the difference between work and heat, and a constructor theoretic understanding of the second law of thermodynamics. The conversation then turns to their recent experiment that tested and corroborated the constructor theoretic notion of irreversibility before discussing future research directions in constructor theory.
All right, I'm here with Chiara Marletto and Vlatko Vedral. Thank you both for joining me.
Thank you for having us.
Thanks very much.
So before we talk about the experiment that you both conducted with other colleagues pertaining to irreversibility in physics, I first want to talk about your result, Chiara, a theoretical result from a paper in 2021. So you discovered a novel connection between thermodynamics and information theory. Now, before we dive into this result, could you please explain why constructor theory is necessary in your view to tackle problems in thermodynamics and information theory in the first place?
The typical problem that one faces when trying to incorporate some entities that are out there in the universe, such as irreversibility or information, etc., in the traditional conception of physics, which is this way of describing things through mainly laws of motion and initial conditions, is that these laws, the laws we know that can work to describe the dynamics of elementary particles and their initial conditions, and then ultimately the trajectory of the whole universe, have a feature that is particular to them, which is that they are time reversal symmetric. So this means that if you look at the evolution unfolding in the forward direction in time, that is as allowed as the evolution unfolding in the backwards direction. So in that sense, these dynamical laws don't have any irreversibility in them. And this, of course, has been a problem since, when we started realizing that irreversibility is, on the other hand, present in nature. And I think the standard way of dealing with this problem in physics is to say that we can still have some laws about irreversible behavior, like what we see in thermodynamics or what we can see, for example, in the biosphere and so on. But these laws are at best approximate, and they're just some kind of emergent laws which only hold in some domain, and they are not really fundamental. The fundamental laws are the dynamical laws. So this is one way of dealing with the problem. But when we go into constructor theory, we see a different way of dealing with the problem. And in fact, this way has been known, in fact, for quite a while. In a way, it's true to the original spirit of thermodynamics, to which constructor theory is inspired in some sense, but hasn't been really fully taken on board so far. And this new way is to say, well, other than talking about trajectories of particles, we can also talk about a different level of description where we're discussing which transformations are allowed, possible in one direction, and which ones are also allowed in the backwards direction. So in this case, when we say allowed, we don't mean allowed in the sense of dynamical trajectories being allowed, but we mean that a transformation has a constructor, meaning an object that can perform it and then stay itself in the ability to perform it again. And when this transformation or task has a constructor in both directions, so a constructor can perform the transformation forward and backwards, we say that is a reversible, physically reversible task. But as you can see, once you shift the attention onto talking about transformations and tasks, you can still have dynamical laws that are reversible, and yet some tasks may be possible in one direction, so there is a constructor for them in that direction. But if you consider the task in the backwards direction, this need not be the case. And this is because, as we know, if you have a machine that can transform something and then you try to use it to undo the transformation, most of the times this machine won't work. And so you can think of fridges and ovens that could be examples of such constructors which can be used to perform a transformation in one direction, but are not as good, or in fact, most of the times don't work at all to perform the task the other way around. Now, this may seem like a parochial switch in a sense, but in fact it's not, because you can then formalize all of these things within constructor theory and see that if you consider the second law as stating that there is an irreversibility of this kind, meaning some tasks are possible in one direction, but they're not possible in the backwards direction, then you can accommodate the second law and its irreversibility in an interestingly exact way within a time reversal symmetric universe, where the dynamical laws are still time reversal symmetric, and this is not in contradiction with there being a law of this kind. And more generally, the conjecture in constructor theory, and this has to do, of course, with the study of the universal constructor and so on, is that all the kinds of irreversibility that we see around us, including those in the irreversibility in the biosphere, for example, can be understood in this exact way through the same route. And this is very exciting. So that's why, switching to constructor theory is a good idea for dealing with this kind of problem. As far as information is concerned, on the other hand, information doesn't have irreversibility built in it. So in a sense, you can have a universe where all tasks are reversible, in the sense physically reversible. So they are possible in one direction and also in the backwards direction. But the reason why, for talking about information and information carrying media, we need to switch to constructor theory is that ultimately, to capture the connection between information that appears like an abstract concept and the physical laws, we need to state what are the regularities that allow a physical system to contain what we usually call information. And if we go into this problem and we try to express these regularities, these are not regularities that are expressible as dynamical transformations or features of the state of a system, but they are exactly expressible as the possibility of certain tasks on these systems. So when we talk about a bit, the fact that it's a bit, it's not due to the fact that, let's say, it's in a given state at a given time, or that it's kind of undergoing a certain dynamical transformation given the initial conditions of the universe, but it's because it can be set to one of either two states, 0 or 1, and these states can be copied. And so you can see I refer twice to counterfactuals because I mentioned two classes of tasks, the copy-like task and the permutation, if you like, tasks, flipping 0 into 1. And it's the possibility of these tasks that makes a bit behave like a bit. And the same can be said about quantum information media more generally. And so again, in this case, we can see that, if you want to capture the regularities of these systems and then say how they behave and what are their general features and incorporate them into exact laws, you need to switch this to these laws that use counterfactuals and therefore the constructor theory.
Now, I understand how the constructor theoretic view can help resolve some of these conflicts between the, let's say, higher level laws of thermodynamics and dynamical laws. And I also see how constructor theoretic framework, but you've also gone further than that in some of your work by unifying concepts between information theory and thermodynamics. So I want to get to the key theorem in your 2021 paper, which says that a work variable is a distinguishable variable. So before you explain what that means, I understand constructor theory uses the concept variable in a slightly unfamiliar way. So could you please explain what exactly a variable is in constructor theory, and then just also tell us what a work variable is in constructor theory, and finally, what it means to be distinguishable in constructor theory?
A variable is a set of attributes that a given physical system can have. So I don't know, if you're talking about a traffic light, color could be a variable, and green and red are, say, two attributes in that variable. Now, variables for physical systems can have a number of features, and the features that I'm interested in for this particular work are whether or not some variables can be transformed in a certain way. So if we can perform certain tasks on these variables or not. And in regard to the particular variables that are relevant for this theorem, we'll talk about two kinds of variables. So the first kind is distinguishable variables. And these are, broadly speaking, sets of attributes of a physical system that can be copied. So again, this is an operational definition of what it means for states to be distinguishable. In physics, we usually take distinguishable as for granted in a sense. So sometimes when we are dealing with, say, classical physics, it's an implicit assumption that any two distinct attributes of a physical system, say two different values of velocity, for example, for a particle, are perfectly distinguishable in principle. And this is a feature of classical physics, but it need not be true in general that different physical attributes are distinguishable. And we have discovered this in quantum physics, where, let's say, there are quantum states that are different physically and yet are not perfectly distinguishable in the same way that the classical physics allows us to distinguish attributes. And so in quantum theory, for example, we say that states are distinguishable if they can be represented by orthogonal subspaces. So this is a formal criterion for telling us when is it that we have a number of distinguishable attributes. But in constructor theory, we can go further than that and generalize all of this notion and saying, well, a distinguishable variable is one that can be copied. And again, we're not saying how this can be done and so on. It's just a definition for what distinguishable means. And it's a very powerful one because it doesn't depend on a particular dynamical law or formalism. And so it allows us to talk about distinguishable states and distinguishability, which is key to information, in contexts where we may not be able to apply the dynamical laws that we currently have, or these laws may be intractable to compute into all the details. So that's distinguishable. Now there's the other kinds of variable that you mentioned, which are work variables. And work variables are a generalization that we can define in constructor theory of the kinds of variables that in classical thermodynamics you would be using in order to do useful work. So from classical thermodynamics, we know that there are different kinds of ways of transferring energy. And some of these ways are work-like. So they are a bit like what happens when we have a spring being compressed and then decompressed in a reversible way. That energy transfer is completely reversible, and it's what could be labeled as a mechanical energy transfer in classical thermodynamics. And then there is a different kind of energy transfer, which is when, for example, energy gets dissipated through friction. I don't know, when you're braking on your bike, then if you're in a non-idealized setting, you will produce some amount of heat on the brakes. This heat is a way to label the energy that goes in a certain way, in an irreversible way, lost. And it can be reused to do further work. Work variable in constructor theory is a generalization of all these variables that in thermodynamics we classify as mechanical means. And these are effectively sources of useful work that can be used in order to do a number of thermodynamics tasks. Now, the connection between these two concepts, a distinguishable variable and a work variable, wasn't pinned down before. And so the theorem that you're talking about is an interesting one, because it says that whenever you have a system with a variable that you can use in order to perform useful work, then you can be sure that these attributes that you're using in order to do work must be distinguishable from one another, in this sense that they can be, in a way, perfectly copied. And this is very interesting, because you see that I haven't mentioned, when stating this, anything that has to do with entropy or other thermodynamics concepts that are statistical. And I haven't mentioned scale. So this connection is very interesting, because it allows us to find a way to connect thermodynamics on the one hand, work, and information theory on the other hand, through the concept of distinguishable variable, in a scale-independent way and in a theory-independent way. And this is interesting because it's like one first result where both thermodynamics and information theory come together in an exact fashion. And it's very different in spirit from other connections between information theory and thermodynamics that we already knew about. For example, those going through the second law of thermodynamics and entropy, because it doesn't need these concepts to be stated. In fact, it only relies on the conservation of energy to be formulated, because the conservation of energy is needed in order to define a work variable. And so this is how, in a way, this result in constructor theory allows you to see that there's an unexpected, surprising connection between the conservation of energy on the one hand and information theory on the other. And I think my colleague Peter Atkins mentioned jokingly to me that I should call this quantity N-formation, to just kind of highlight how this result somehow gives us a surprising connection between energy on the one hand and distinguishable variables on the other. And so in a way, it redefines energy as a particular kind of information.
Right. So regarding this unification between information theory and thermodynamics, and I appreciate the fact that you said it's scale-free. So I'm wondering, does this theorem have implications for future engineering technologies for humanity? And I say this because part of the reason thermodynamics is sometimes a problem is, as it's traditionally formulated, is because it's not scale-free. But when you're interested in technologies like nanotechnology, you have to understand the physics of thermodynamics at very small scales, maybe even quantum mechanical scales. So do you think your theorem will have a significant impact on the future of engineering?
Yes, this is of course, this would be a kind of long-term vision, because this is, as I said, it's a very abstract result at this stage. I'm hoping that this can be used in order to design generalized engines that, on the one hand, generalize the idea of a constructor, a more general constructor, not just a heat engine. And the other, they also generalize the classical heat engines, where there are usually, one has to assume the presence of things like heat baths that are these very large reservoirs of many particles at a certain temperature and so on. And there is a current branch of, let's say, spin-off of quantum information, which is called quantum thermodynamics, where people have been exploring ways of extending the results of statistical mechanics to the quantum domain, to regimes that are not the thermodynamic limit, as well as non-equilibrium situations. And those results are still somehow rooted into the formalism of quantum theory. And what I'm hoping is that because this general result I just mentioned doesn't rely on quantum theory's formalism, and is much more similar to the original thermodynamic statements that, say, Kelvin and Clausius made, where they were trying to be, in a way, dynamics free or theory free, so they were not kind of relying on a specific formalism. I'm hoping that this result will supplement these other interesting results in the quantum thermodynamics domain and make them even more general than they are now. And this is important because we expect one way or another that quantum theory as we know it will be modified in the future, if not for anything else, just to incorporate gravity. And although we expect at least I expect most of the features of quantum theory to stay as far as information theory is concerned, so things like entanglement, superposition, etc., and maybe more weird things to also appear, the formalism may be different. And so we need some general ways of talking about these thermodynamics concepts that are not just scale independent, but also theory independent. And this result that I mentioned is very much in this spirit. And I'm hoping that there will be more results to come in that direction that will inform new technological breakthroughs, possibly generalization of the universal quantum computer along the lines of what von Neumann had in mind with the universal constructor.
That would definitely be very exciting. So before we switch over to the experimental work that you both have done along with colleagues, I think we should leave listeners with a couple concrete examples of physical systems that could illuminate your theorem. So what's one example of a physical system with distinguishable attributes from which we can extract work? And then also, what's an example of a system with attributes that we cannot distinguish from each other and so cannot extract work from?
So a classic example is of the former kind is a battery with two or more energy levels. Now, if this battery is idealized, we can think of these two energy levels as discrete and separated from each other by quite a finite amount, a finite energy gap. And if you imagine a system that extracts energy from the battery to perform a certain transformation repeatedly, in a way that's reliable, then this process of extracting energy in order to perform a work in a reliable way, in fact, is a way of distinguishing these two energy levels of the battery. So that's a very, very simple example to understand why the possibility of extracting work reliably from two or more states or attributes, in fact, is an indirect way of distinguishing them and ultimately of producing more copies of them. Now, if you think of a quantum system, so supposing the battery is quantum, and therefore it can exist in quantum superpositions of these two energy levels, then you can think of lots of states that are not these two energy levels, but they are, as I said, they are superpositions of the two energy levels. And now those also have an energy. You can define some average energy. But if you now are wondering whether you could likewise use your machine that can extract work from the two original levels to extract fully that energy in a one-shot experiment, then you will see that you can't do that. And you can't do that because if you were able to do that, then that would violate the very basic principles of quantum theory that say that this superposition of two energy levels is not perfectly distinguishable from the two energy levels in question. And so this is an example of a system where there is a third or even more states that are physically distinct from the two energy levels that we started discussing, and yet are not perfectly distinguishable from either of those. And despite having an average energy associated to them, these states can be used in order to produce work deterministically. They can be used in this way if you had lots and lots of copies of the same system, and then you had a way to address all of these copies And in the infinite limit, you could in principle extract this average energy. That's the meaning of average energy. But if you're really talking about one single system, one battery, and a quantum superposition of those two energy levels, there's no way you can extract work deterministically out of that repeatedly without violating some features of quantum theory. And so there's kind of a second type of system to match your question.
Yes, thanks for that. I think that'll be very helpful for listeners who are trying to understand this very novel theorem and new way of looking at information and thermodynamics. Now, going back to what we had originally talked about, which was irreversibility. So, Vlatko, I'd like to bring you in now. And before we talk about the experiment, Vlatko, what is the latest formulation of the second law of thermodynamics in constructive theoretic terms? And could you please tell me why it is helpful in solving problems to express the second law in constructive theoretic forms? Because certainly the second law has been expressed for a long time in a few different ways.
Yes, Logan, you're right. Actually, it's a very long-standing question in physics to understand where the second law really comes from, because it claims that energy conservation is the first law, of course. And as Chiara says, it's an exact law. It applies to all situations. It does not matter whether it's a micro or macroscopic system, the constituents, it should apply to all situations. However, the question with the second law really is it as universally applicable as the first law? And that's exactly what Chiara has nicely explained, that somehow the idea with constructors is to phrase this in the same way, so that it really applies to all physical systems equally. Traditionally, in physics, you would think about the second law in some kind of lossy manner. So let me just explain this a little bit. If you were to try to get some energy by, let's say, exciting your atom, you could shine some laser light, the electron inside the atom could go from one level to another level. Therefore, it would use this energy to basically increase its own energy. And you can think of this, even though it's a basic atomic physics process, you could think of it thermodynamically. But now, what second law stipulates in some sense is that whenever you are doing anything of this kind, there will be something lost in this kind of process. And the question is, where is this lost? You could be thinking, well, maybe when you move a charge from one place to another, it disturbs all sorts of other charges in the neighborhood. And it creates certain noise, certain friction within the environment, which actually leads you not to be able to do this over and over again. And I would say all our traditional approaches are actually of this kind. There's always something that's lost. Either you don't have enough information yourself as to what happened to this extra degrees of freedom. You can say, oh, I can control the electron in the atom, but surely I'm not able to control all the other charges, all the other atoms and molecules that may be there involved in this kind of interaction. So somehow physics has traditionally thought about this in this way, that it's because we are not either able or because fundamentally we cannot maybe track all of these interactions. And of course, the more complex the system gets, the more ways in which this kind of energy could be lost, which is why we think of thermodynamics traditionally in the macroscopic domain. But now constructor theory brings a new component to that. That's the whole point of this, to try to come up with a different explanation that's not, oh, we lost energy in some degrees of freedom, we don't know where they are, which is incidentally tantamount to losing information. It's basically you not being able to track all of the interactions within your system. And I think most of us always think of Boltzmann, who kind of tried to explain the second law in all sorts of ways of this kind. And now what Chiara has been actually saying and promoting is that maybe we should think of it differently. Maybe we should acknowledge that the basic laws are fully energy conserving. They're fully reversible in principle. The dynamics in one direction is as good as the dynamics in the opposite direction. There's nothing wrong with it, really. It's physically possible. But actually what happens is that as you try to utilize this constructor in a closed manner, namely that you are able to repeat the same cycle over and over again, you may actually reach a point where in one direction this proceeds at a certain rate, whereas if you were to do this with a constructor in a backward direction, you will be less efficient than in a forward direction, even though the laws of physics that underline all of this are actually fully reversible. So they don't see that difference. But if you phrase it in terms of constructors and closed cycles, suddenly this discrepancy comes up. And in fact, that's exactly the experiment that you alluded to. It was really more a proof of principle to try to test exactly this kind of irreversibility.
I think one way of repeating what you're saying, Vlatko, is that even though it's possible for a constructor to take a glass on a table and push it over to the side and break it, and it's also possible for a constructor to, in principle, to pick up the pieces and reconstruct the glass, it's not possible to do that without side effects. And so I think in constructor theory, the difference between, let's say, work and heat and whether a task is possible with or without side effects elucidates the second law of thermodynamics as it applies to physical systems.
Yeah, that's a perfect way of putting it, actually. And your example is excellent because that's the one that you most frequently read about in popular expositions of thermodynamics. That, namely, if you accidentally break a glass, that to us somehow sounds like a far more natural process than the glass spontaneously reassembling and going back into the original position. We never see anything like that happen, even though, as you said, all the laws of physics would be perfectly reversible. And you can imagine trajectories of each of these atoms simply going back and reconstructing the original glass. There's nothing wrong as far as Newton's laws or even quantum mechanics laws are concerned. So you're right. It's simply that the constructor going in the backward direction is less efficient. And that's what gives you this fundamental uncertainty. In fact, if you go back to someone like Planck was very, very keen to express, even though, we call the original formulations of second law, we attribute them either to Carnot or to Kelvin or to Clausius. These are the three names that you will keep hearing. None of them really, if you read it more carefully, phrase them in the way that Planck did, which is to emphasize this cyclic nature. Can I really do this in a cycle, and therefore can I reuse this and do it over and over again? That's the whole point. You want to be using your constructor over and over again. And as it happens, when you do that, then suddenly you start to see the difference between going forward, if you like, and backward. One direction somehow becomes less efficient than the other one.
Right. Now, getting to how you demonstrated this experimentally, you used a device called a quantum homogenizer as your kind of toy model. So yes. You were thinking of the constructor theoretic notion of irreversibility with the quantum mechanical laws of motion in this case. Now, I suppose in principle you could have used different laws of motion, but in this case you chose a quantum mechanical system. I just wanted to highlight that. Now, so why was the quantum homogenizer such a useful toy model for this, and how exactly did you demonstrate the constructor theoretic irreversibility using this quantum homogenizer?
You highlighted a number of interesting points there, actually. Certainly one of them was this issue that you do the experiment quantum mechanically, and it's something you touched on with Chiara as well, whether quantum physics really gives us a genuine new element to quantum thermodynamics. Whether being able to prepare superpositions of different states and utilizing quantum coherence does actually give us an extra advantage with respect to classical systems. And I think that's why we really went with the quantum mechanical experiment rather than the classical. Needless to say, given that we anyway know that classical physics is kind of a special case, a special limit of quantum mechanics, then of course the same conclusions could be drawn for a fully classical system. So I think the experiment could have really been done with classical systems, and I think you would see very much similar conclusions, broadly speaking. Of course, you wouldn't have the superpositions that you have in quantum mechanics, so that would be the key difference. The systems we used, they're really a proof of principle in the sense that you wouldn't naturally use this as a real thermodynamical engine. No one would really suggest that this would possibly be useful to really extract some work in a kind of efficient manner. So it was really more like a proof of principle, and it involved a very small number of quantum bits. In this case, we were talking photons. So basically, the reason why a small number of photons was used is simply because it's very difficult to control these photons in a coherent manner if there are too many of them. I think even the best labs in the world would not be doing more than 10 photons at the same time. That's kind of the state of the art as far as quantum computing is concerned. So the group of Genovese in Turin, in INRIM, what they did is they encoded the degrees of freedom of the qubit onto the polarization of these photons. So the photons, because they are, of course, particles of light, and light is an electromagnetic wave, then each photon can really oscillate, if you like. The electric field pertaining to this photon can oscillate in one direction or another, two orthogonal directions. We call them usually horizontal and vertical. And these are your logical 0 and 1, if you think of them as quantum bits. Now, what does this word homogenizer there really mean? It means that one of these systems is going to be the medium, if you like. Now I'm using the thermodynamical language. It's going to be your work medium, so to speak. It's the system that's going to interact with other three photons, which constitute an environment from which you somehow want to extract the work. But at this level, actually, you should be thinking probably slightly differently to this. What you're really thinking is that as your system, as your single photon interacts with each of the photons of the environment, what it actually does is swaps its state with the state of the environment. So here you should be thinking more in terms of kind of quantum information theory rather than thermodynamics. Although, as Chiara was saying, the two are, of course, intimately related. And that's the whole point, the relationship between information and thermodynamics. But basically, here the idea is you start one photon in one state, and you start the other three photons in a different state. And then through interactions between this single photon and the other three photons in succession, one after another. And that's where the difficulty of the experiment really lies, to time all of these, synchronize them to happen, and so on. What you actually end up achieving is that your single photon, the system, the medium that does the work, ends up actually ultimately, finally, in the same state as the environment. And you can now say, well, wait a second, where does this irreversibility come in? And the clever idea there is really to swap. So you repeat this experiment that I described, but now you swap the states of the system and the environment. You prepare the system initially in the same state as you did the environment in the previous experiment, and vice versa. And then you run the experiment again. And what's interesting, and again, we are emphasizing the fact that the laws of quantum mechanics are one and the same. For both of these situations, they're perfectly possible. You can apply them to both of these cases. What you actually see is that this swap of the states happens more slowly in the backward direction, if you like, than in the forward direction. So one of these directions is less efficient, if you think of this swap as the task that you're trying to achieve, than the other one. And it's interesting, it was interesting to us that even something as small as this engine would already start to show this kind of discrepancy. Obviously, what Chiara and I have done is to do calculations with a larger number of these systems. And obviously, the larger you go, the more amplified this distinction becomes. But it was very exciting to us to see that even a proof of principle experiment with 4 photons altogether already starts to demonstrate this.
Yes, and this goes to if constructor theory is correct, or at least if the principles that you both are applying in this case are correct, they should be scale free, going to your point that it shows up so early, so to speak.
Exactly right.
Yeah.
Exactly right. So someone would call this a micro engine, if you like, or people talk about nano engines as well, depending on the scales. All of them should really be described by exactly the same laws of physics. That's the punchline really here.
Yes. Now, regarding the predictions that you generated for the experiment, were you able to produce those predictions with the help of constructor theoretic principles, or did you create them only using a quantum mechanical framework with the constructor theoretic principles in mind?
The specific predictions for the experiment were a combination of the formalism of quantum theory that was needed to make the exact quantitative calculations, as well as of these general principles of constructor theory, because those principles guided us to find the measure of this irreversibility. So when we said that the constructor in one direction was less efficient than in the other, the measure that we used in order to check this fact was a measure of efficiency guided by this intuition of constructor theory's general take on these things that has to do with how do you define a task to be possible. And so in a way, I think the result was really a combination of these two theoretical tools. And as always, when you're quantitative about some predictions, you do need ultimately dynamical laws to make calculations. But just like with other principles, the intuition for how to use them and what to compute and so on comes from the higher level principles. And I think this paper is a bit like that. It has both in them. And this is why it's exciting, because somehow it's the first, maybe one of the first cases where we combined the laws of quantum theory with these higher level principles and got something interesting out of that.
Yes, and I think just to add to that, the point really is that you could apply exactly the same logic to any system. It could be, like I said, obviously classical, because we know classical physics is a special case. When you kind of delete all the superpositions, you end up getting classical bits out of quantum bits. But I think what's interesting here is actually that you could become super quantum as well, because we don't know whether quantum physics is our ultimate and final description of nature. And the beauty of, I think, this way of phrasing it, it seems to me that it has a chance to survive even the next theory, as it were. So even if something were to supersede quantum physics, I don't know what, quantum theory of gravity that really gives us something completely new, it seems to me that this kind of behavior would still be intrinsic to this new theory. Obviously, the experiment you'd be then doing would be very different to this experiment that we were part of. But I guess the overall logic would be one and the same. And I think that the universality here is really beautiful.
Yes, I agree. I think it's a little bit counterintuitive, at least for now, to have a kind of theory of principles that themselves constrain what dynamical laws of motion are possible or are consistent with those principles. But I imagine that will change should the constructor theory program continue to succeed and become more and more taken for granted by researchers. So one more question regarding kind of the experimental results. What outcome of the experiment would have been problematic for the constructor theoretic notion of irreversibility? And feel free to answer qualitatively or quantitatively.
Thanks. Yeah, I think it's clear that the experiment could have gone the other way. It is certainly feasible. I think here the idea that if you start the system in one quantum state, let's say a pure state, and if you start the environment in a mixed state, which would be kind of maybe how you think about this normally in thermodynamics, and then you see that the dynamics proceeds with a certain efficiency, and then you swap the two, it could, of course, logically be that you get exactly the same convergence. Maybe the same behavior would take place. This certainly would not be very good for the constructor theory outlook, because I think constructor theory would say that fundamentally somehow these two, or at least there must be two directions which somehow would really give you a quantitative difference here. So I think it's easy to imagine an experiment that would fail in this case. Of course, there are states that would actually behave the same. This doesn't exclude that there are some states that would behave the same way in both directions. And in fact, we have examples of such states ourselves. But the key is here that you can find other states that actually would exhibit this kind of difference. So that would be one certain way in which the experiment could have kind of violated, I suppose, this view.
And I suppose, let's say the outcome of the experiment was problematic for the constructor theoretic notion of irreversibility at the scale of your experiment. A quote-unquote naive defender of constructor theory might say, well, but if you just have a higher scale, it'll apply. But the whole point, as you were saying, Vlatko, is that the constructor theoretic principles are universal and scale-free, so they better work at all scales.
Yes. I'm afraid that if you took that first line of defense, you'd actually be going back to the traditional way, as I said, that it's really due to some kind of friction that adds up with more and more systems or some loss of information. Then I agree we wouldn't be able to defend the constructor theoretic way of doing this. Yes.
Yes, and in your example earlier about the glass, right? The traditional take is to say, oh, it's so unlikely that the glass could reassemble itself spontaneously. And, going along this explanation that you just suggested would be a bit like that. And so it would be kind of cop out from the idea that you're kind of trying to say something more than just traditional statistical mechanics.
Yes. Yeah, of course, there is the most boring possibility that the experiment wasn't done properly, but we're discarding that. I think these are great guys, as you will find out, and I don't think they made that kind of error.
No, they wouldn't make that mistake.
Yeah.
Yeah, no, I specifically didn't even consider that possibility.
Yes.
Right. Okay, so final question. Now that this experiment's results seem to have corroborated the constructor theoretic approach to irreversibility, what open problems in physics are you next interested in solving using this constructor theoretic notion of irreversibility?
To me, well, there are many problems. I think there is this interesting work I'm doing with the student here in Oxford, Maria Violaris. She's interested in applying this logic to erasure. So trying to revisit the traditional paradox of how is erasure possible in a finite universe and how is that connected with the Szilard engine and so on. So I think that's in a way, it's a small step further in the same direction. So trying to make some of these considerations about Landauer's principle, the cost of performing erasure, more exact than they are at the moment, where actually Landauer's principle is somewhat a consequence of this statistical second law, and therefore it's not scale independent, etc. But more generally, I think what is really fascinating to me is to try and use this as a first step of this bigger theory about programmable machines and programmable constructors that could be a bit of a hybrid between quantum computers and biological systems, and find a set of laws that describe the way they work and the physical limits, the ultimate physical limits, in the same way that the traditional thermodynamics describes the limits of heat engines. And so in a way, we don't have that yet, but I think it would be very interesting, and it would also be fundamental for having a new take on complexity theory, which is a branch of computer science and partly maybe of physics too, that has always been a bit too idealized and hard to apply exactly in biology, for example. Whereas with this new take on irreversibility, I'm really hoping that we can get a handle on these problems that's more physical. So David Deutsch, on the one hand, is working on the universal constructors ideas, and Sarah Walker as well is kind of leading some studies into the biological side of things. And so I'm really hoping that these tools that I developed could be useful to them too. So that's the ultimate frontier, I would say, that we're aiming for.
It seems to me that this is the most exciting question in science, right? From kind of micro to macro. Can we really connect the laws of nature in this way? And rather than have them only apply to physical systems, to chemistry, to biological systems, and so on, could there be kind of a unifying framework for all of this? Could we really take the laws of physics out of this micro domain and really see how they apply to more complex objects? And it seems to me that's kind of what excites me the most, right? That there is a hope that we can unify all of these disciplines. That would be amazing, I think.
Yes, and I think there is one thing that you, Vlatko, like a lot, which is this trying to have a better understanding of this transition from non-life to life.
That's it.
Right.
Because it seems to me still, notwithstanding the theory of evolution, which, seems scientifically really well established, somehow it does require a certain beginning. It requires a certain complexity initially in order to kick in. We need kind of replicators or constructors maybe of sufficient complexity on which then the laws of evolution would do their work to produce something even more complex. This earlier transition before that, when chemistry, if you like, becomes biology, it seems to me completely unclear. We don't really understand this well at all, to the degree that some people are saying even new laws of physics might be needed to explain this. Now, to me, somehow it seems more likely that maybe this principle-driven constructor theory logic would actually suffice, possibly even given the current understanding of quantum mechanics. And this really excites me the most, I think.
These are all certainly extremely ambitious and exciting research areas. So I look forward to reading your papers in the near future, and I thank you both very much for your time.
Thanks a lot, Logan.
Thank you very much, Logan. Yeah.
Thank you.
That was Chiara Marletto and Vlatko Vedral speaking with Logan Chipkin. We'll be putting links to papers describing both the theory and the experiment on the podcast page, fqxi.org/community/podcast, as well as links to earlier editions of the podcast featuring interviews with Marletto and Vedral. That's all we have time for. As always, you can contact us at FQxI on Twitter, where you'll also find Logan at ChipkinLogan, or you can reach us via email at podcast@fqxi.org. We're also on Facebook and Instagram at FQxI Physics. And don't forget to subscribe to the FQxI podcast to hear the next instalments in the Conversations on Irreversibility series produced by Logan. Thank you for listening. I've been Chiara Marletto.